तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back all of you to the lectures on computer graphics. Today we start the discussion on three-dimensional graphics or three-dimensional computer graphics. If you remember, in the last few lectures we have been discussing various types of transformations in two-dimensional graphics, and now we will see how to represent and perform those operations in 3D, and that is the basis of three-dimensional graphics. The most important difference between two-dimensional graphics and three-dimensional graphics is that in case of two-dimensional graphics, we did not have any concept of depth variations of the object with respect to the viewer. That means, all the object which we were viewing did not have any depth, and it was on a two-dimensional planar surface, and we did all the operations in an x and y plane or an x and y domain. Now we have the z component on the coordinate system. That means the object is a three-dimensional object. So basically, what was a square, let us say, has become a cube. What was a circle has become a sphere. If it was an ellipse, it has become an ellipsoid in 3D. And not only that, the object has been turned from 2D to 3D, but we have to worry about projection geometry for the first time in three-dimensional graphics, which had no scope in 2D. That means, when you take an object and bring closer to you or to closer to a camera which is viewing it, the object size becomes larger, and when you take it away, it appears to be smaller due to what is called the foreshortening effect. That means, larger objects may appear smaller if they are far away from you, and small objects may become closer may appear larger if you bring them closer to you. A typical example could be, if you take a ball, a tennis ball or a football, and bring it quite close to you in front of your face, you will see a very large volume. Whereas if you probably keep looking at the moon, which is of a very, very large size, it typically appears very small because it is very far away from the viewer. So that is the effect of depth or zooming, which comes in projection geometry, or what is called as perspective projection geometry. We also have oblique projections. We also have orthographic, different type of projection geometries we will also study, but we will first analyze the three-dimensional coordinate system and see whatever transformations we have done in 2D, what happens if we just push them to three-dimensional coordinate system and apply the similar transformations. So, we look on the screen, we first look into three-dimensional graphics and we talk of a coordinate system. We usually use a right-handed coordinate system, as you can see in the maths. It is called a right-handed coordinate system because you can open the three fingers of your right hand, the palm, the thumb and the index finger and the middle finger, and in an orthogonal directions, and each will represent x, y and z respectively. And as you see on the screen, similarly you can do this with your three fingers, and that's what you get a right-handed coordinate system. You can also have a left-handed coordinate system. When you open the three corresponding fingers on your left hand, you will have a left-handed coordinate space x, y and z. In 2D you had only x and y, but in 3D you can have x, y, z. So, you have translation along x, y or z, and also you can have rotations about these axes. We will see those transformation matrices later on. And the left-handed system is suitable for the screen geometry, where the x-axis moves from left to right in increasing x values, the y-axis moves from bottom to top, and the z-axis goes from the viewer into the screen, whereas in the right hand space the z coordinate is pointing towards you, if you take the x and y coordinate systems to be the screen. To transform from left to right, you just negate the z values. So, basically the z axis changes direction from right to left coordinate system. Okay. So, assume you can visualize the two different coordinate system. You can take any one of them, and but you should be consistent with the mathematics you are using, the transformations. So, possibly right handed coordinate system is very natural. If you feel that is very natural to you, you can use that. Okay. And if you remember, a point in 2D was represented by two coordinate x and y. In 3D you have x, y and z, and we know now, I do not think you have any doubts of why we need homogeneous Cartesian coordinate system or a homogeneous representation of a point. The basic reason was, you remember that we had to represent translations also as matrix multiplication, as like rotation, reflection and etc. And so, you take a homogeneous coordinate system. So, in 2D we had 3 parameters, and for 3D we have 4 parameters, where W is the homogeneous parameter, which is typically taken for as 1. Otherwise, you divide the first 3 by W, you basically get back the actual coordinate system from the homogeneous Cartesian coordinate system representation. And P is a vertical vector, basically x, y, z, w transpose. So, it is a vertical or a column vector, and when you take it as a column vector, typically you pre-multiply the matrix P by a transformation matrix A. We talked about this in 2D, similar concepts hold in 3D as well, and you get a new coordinates P prime. Of course, if you take the P to be a row vector, that means the P is equal x, y, z, w without the transpose. If it is a row vector, then what will happen is P prime becomes P multiplied by A, or P gets post multiplied by the transformation matrix A. Now, let us look at the transformation matrix A as to how it looks like. Okay. And the generalized transformation matrix in 3D will now basically be a 4 cross 4 matrix as given. So, it will have 16 elements or 16 parameters in it, and you remember in 2 dimensional coordinate system and 2 dimensional transformations, when we were dealing with homogeneous Cartesian coordinate system in 2D with 3 parameters, we had a 3 cross 3 or 9 elements. Now, since we have 4 parameters including the homogeneous parameter H or W as you can call it, you typically need to have 4 by 4 or 16 elements. Okay. So, if you look at the screen now, we have the A, capital A matrix with 4 cross 4 elements A, B, C, P, D, E, F, Q and so on, and what I do is I represent this matrix A by what I will call as partition matrices. Okay, partition matrices T, K, tau, capital Tau and capital theta, where the capital T is a submatrix or a partition matrix of A, or basically you can say it is a submatrix of A consisting of the top left 3 cross 3 elements or 9 elements from the T, and these elements of T are responsible to produce all the transformations, all linear transformations including scaling, shear, reflection and rotation. Okay. So, as like we had a 2 cross 2 in 2D, we have a 3 cross 3 which produces all your transformations, and this is a just the parameters. We will see the expressions of these of T as we go along for different types of transformations. They are almost similar with an extension of one more parameter. We will basically talk more about scaling, reflection and shear, and we know that depending upon the diagonal elements and off diagonal elements, when it will cause shear, when it will cause reflection, scaling and so on. Okay. Now, T is responsible for all these linear transformations. What about the remaining 3 submatrices? We have K, we have tau and we have also have the capital theta. The K, which is again a vertical or a column matrix PQR, is responsible for the translation. Is responsible for the translation component in 3D. Capital tau or gamma, as you can call it, is now a row vector LMN. It yields a perspective transformation, although you can visualize this to be a column vector, but typically it is the last row of A, the first 3 elements of the last row. They are responsible for yielding the perspective transformation. So, they are responsible for the parameters of of perspective geometry. We will see that as we go along. And the last parameter S, its name that is why it is put as S, is responsible for uniform scaling. This also show, if you recollect your thoughts and concepts and equations of two-dimensional transformation matrices, the bottom right diagonal is always responsible for uniform scaling in 2D. In this case, it is responsible for uniform scaling in 3D. And again, of course, I should repeat that you can use the parameters of the T matrix, that is the upper left triangular 3 cross 3 submatrix T, and you can also play with the diagonal parameters A, E and J, A, E and J of the T to also use non-uniform scaling or uniform scaling also as required. But if you just want uniform scaling, you can play with you can use the parameter S without bothering about the other parameters. So now we know that upper left components are responsible for scaling shear reflection, the PQR right vertical parameters of the last column are responsible for perspective transformation, and the last row LMN responsible for perspective transformation. K, I repeat, PQR is responsible for translation. Okay. So now we look into some special forms of this transformation matrix A, and this is a simple example of translation where I change the PQR in the previous matrix to corresponding parameters Tx, Ty, Tz respectively. In 2D translation of 2D transformation category, you had only Tx and Ty, that is translation along x and y respectively. Here you should have the translation parameters along x, y and also z. So that is why you have Tx, Ty, Tz as the 3 parameters for translation. Okay. You also can talk about scale, uniform scaling, uniform zooming, compression or enlargement as we talked about in 3D, and in 2D we can do the similar thing in 3D, and you can play around with Sx, Sy and Sz to produce non-uniform scaling along x, y and z respectively. Okay. So that is how you control the scaling of 3D objects with the help of 3 different scaling parameters. Yes, you can use shear, and as you see here, off diagonal elements responsible for shear, and you can do the following by shearing with respect to x, y and z. You can vary these corresponding parameters in the off diagonal submatrix T to produce shearing effect along x, y and z respectively. So this is how you see. You can please write the matrix form in terms of P prime equals A primes P. When you shear along x, basically what you are doing is you are creating the corresponding change in the corresponding coordinates. Okay. Origin of course is always affected by unaffected by scale and shear. So if you have the origin of the 3D and if you give any value of x, sy, z or the shear values, the origin does not change. Origin of course can be translated, but it cannot be scale or shear. So these are simple examples of translation, scale and shear submatrices, and we go into 2 major types of transformations, linear transformations, and the upper submatrix T is responsible for the linear transformation. So we will look at reflection matrix, and the following matrices are responsible for reflection. Now you remember when we talked of reflection in 2D, we talked about reflection about a line. Okay. And here in 3D we actually talk about reflection about a plane. This is true with respect to the reflection which we actually see over a mirror, and we put a mirror in front of you. Actually you can see the reflection of yourself on the mirror or for some other object, and the reflected object actually appears behind the mirror. So you are looking about a plane, you are looking at a reflection across or about a plane is what you are looking at. So in 3D we talk about reflection about a particular plane, and these are special reflection matrices which talk about reflection about the xy plane. So Txy as given by the expression on the left hand side matrix will produce a reflection about the xy plane. Tyz will cause a reflection about the yz plane. and Tzx will cause a reflection about the Zx plane. If you look at the nature of the matrix in each of these cases, it is actually an identity matrix, close to an identity matrix, not equal to an identity matrix, but it is except one of the unit values in the diagonal elements is made negative from +1 to -1, all others are +1. So, depending upon which plane you want to get reflected, if you want to reflect about xy plane, you want to negate the values of z. So, that is why you have in the third row, third column intersection the one change by polarity of the value of 1 change to -1, or you put a -1 there. If you want to reflect about the yz plane, basically the values or x coordinates of the points of the objects become negative. That is why you have the intersection point of the first column put as -1, and if you want to reflect about the zx plane, you basically need to negate the values of y coordinates. You want to negate the values of the y coordinates, so you change the second row, second column intersection value is changed from +1 to -1. That will cause, after the multiplication with p, the y coordinates will change, become negative. So, you can visualize this, that the corresponding matrices will cause the reflection about x, y, y, z and zx plane respectively. So, these are reflections about specific coordinate planes, as we had reflection about a line in 2D, and we will also look into reflection about a general plane, arbitrary plane in 3D. But before that, we will look into another form of which is the most important part among I should say, as far as mathematics and concept is concerned, is about rotation about an axis. Okay, so, rotation as like reflection also we can form specialized rotation matrices to rotate about the orthogonal axis, that is x, y and z respectively, and we will first look at the specialized form of those matrices which will cause rotation about x, y and z. Okay. So, let us look into the screen. As you see, the first rotation matrix example is given. This will cause rotation about the x axis. As you can see, this form is very close to the rotation matrix in 2D. The only difference, or the main difference, is that it was a 3 cross 3 matrix in homogeneous system in 2D. It is basically a 4 cross 4 matrix in 3D, because the inhomogeneous unit you have 4 parameters, and in 3 cross 3 if you remember there were of course the cosine alpha minus sine alpha. Alpha is the amount of rotation about a particular point or the origin. In 2D now we are rotating about the x axis. So, when you rotate about an x axis, now you have to visualize yourself that we talked of a right hand coordinate system. You talked of a right hand coordinate system, and let us say this is your x axis, which is the middle finger, index and y respectively, let us say y and z. If you look into this, visualize yourself with a scenario in your right hand coordinate system where you have the y and z as your, say, the thumb and the index finger, and the middle finger represent your x axis. So, when you rotate an object about an x axis, okay, if you try to visualize yourself that you are rotating about the x axis, okay, this is your x axis, let us say y is pointing towards you and the z is pointing up. Actually, ideally you would like to have a scenario where the z is pointing towards you, that is also okay. Z could be pointing towards you, this could be x, this could be y, there is no problem. Y is vertically up, z is pointing towards you. Let us say this is the x axis. If this is the x axis of your coordinate system and you have to rotate an object about the x axis by an amount theta, whatever the amount theta may be, plus or minus, that means clockwise or anti-clockwise, you can see I will rotate the coordinate system now. What will happen when you rotate around the x axis amount a particular axis, the x axis value remains unaltered for the object, but the y and z coordinates change. Y and z coordinates of the object, take a particular point, rotate about the x axis coordinate remains same, but the y and z, this is, let us say, my y axis, this is the z axis. So, if you rotate about the x axis, which is now, say, now pointing towards you, what do you have basically is the y and z coordinates change. Okay. So, that is why if you look into the matrix form in the screen now, the second row and the second column are the places where the cosine alpha and the sine alpha parameters are put, basically, which will cause the change in the coordinates of the y and z value depending upon, of course, the amount of alpha. Of course, if alpha is equal to 0, you can very well see that it becomes an identity matrix, because it will not cause any rotation. So, you have seen x axis. Let us look into y axis. rotation about an y axis, you can also visualize in a similar manner that whatever axis you are rotating about, the coordinate of that axis will never change. Okay, you are basically doing a two-dimensional rotation in some sense. Okay, and that means around when you are rotating about the x axis, you are doing around y and z, like in 2D, x and y you had done. Okay, and that x and y has become y z when you are rotating about the x axis. Now, when you are rotating about the y axis, the x and z coordinates are the one which will change, and hence the parameters are put around the first and second rows and first and third, I repeat again, first and third columns and rows of the corresponding matrix, because those are the coordinate values x and z respectively which will change when you rotate about the y axis of the three-dimensional coordinate system. So, now you can visualize that when you rotate about the z axis, you get actually the form which you had seen in 2D, because now what will happen is when you are rotating about the z axis, the z coordinates of the point will not change. What will basically change is the x and y coordinates. So, this is exactly like 2D rotation, where the z axis was coming out in a plane in 2D and you had x and y on a plane, and you were making a rotation about the origin with the z axis pointing out of the plane towards you, let us say, or out of the screen towards you, and you are moving from x to y or y to x. Those were the coordinates which were changing. So, basically rotating around the z axis is almost notionally equivalent to the rotation in 2D which you performed, because the z axis values will not, or the z coordinates value will not change now, but the x and y coordinates will change. So, combining these three, I think it should be easy for you to visualize that. I repeat again, rotation about x axis, x coordinates will not change, y and z coordinates will change. Rotate about y axis, y coordinates will not change, x and z coordinate values will change, and lastly, rotation about the z axis will cause change in the values of x and y coordinates, but not the z coordinates. So, this is the concept of rotation around any one of the orthogonal coordinate axis. An important property which we have to spend time here, I am not sure whether you have noticed, is with respect to these three matrices which have been basically borrowed from the concepts of 2D rotation, all right. There is one sign of alpha or beta or gamma where the sign is changed, that we know why, because this concept came from 2D. But you see here the position of the sign is different in one of the cases, that means the sign is reversed in one of the cases. Why? Let me try to give you what I mean here. If you compare the position of the negative sign of the angle of rotation, it is at the same position with respect to, I am talking of the relative position of the cos alpha sin alpha terms. Just consider the cos alpha cos and sin terms, and do not worry about the zeros and ones in the corresponding matrices. If you see the matrix form for rotation about x axis, and if you see the corresponding one with respect to z axis, they are almost similar except the position depending upon the axis, all right, but the negative sign is same, that is on the top right sign of whatever angle. But if you see the rotation about the y axis, the sign is here, on the bottom left instead of being on the top right. You see, with respect to x axis it is top right, with respect to z axis also is top right, but with respect to y axis, instead of being on the top right here, it is on the bottom left. Now, there is a reason, it is not a mistake, this is a reason why this is so, okay? And we will see, we will spend a little bit of time, you should know why this is so, because otherwise if you write these equations and implement using a program in C, you will make a mistake by putting the sign at the same position in all the three cases. That is not, okay. So, let us see why this is so. We come back to three-dimensional right-handed coordinate system, as you can see here x, y, z, and those arrows mark the rotation. Now, let us take the rotation about the z axis. When you rotate about the z axis, the rotation is from x to y. This is given in the three-dimensional figure here, or also on the left hand side bottom figure, where you have to visualize that the z axis is coming out of the screen towards you. The z axis is coming out of the screen towards you, and So, when you rotate around the z axis, now the rotation sign, if you carefully see of that curved arrow which is put in the 3-dimensional scene, you can visualize this in the following manner. I will ask you to do the following. In the right hand coordinate system, what I will ask you to do is you grab this axis, okay? You grab this axis by the right hand. Okay, let us say this was the axis which was pointing, say it could be x, y or z, whatever. This is the axis which is going, and you grab the axis yourself using the right hand. The direction of the thumb points to the positive direction of the axis. It could be x, y or z. Suppose if this is the axis pointing upwards, if you grab the axis, the direction of the thumb will point in the positive direction of the corresponding axis, and the direction of the rest of the fingers actually point in the direction of rotation. A point in the direction of rotation, it could be, that means if you take any one of, you can take any one of the axis x, y or z of your right hand system, grab any one of these axis with your right hand. If you grab with your right hand, the thumb points towards the direction of the positive axis away from the origin, and the rest of the fingers point in the direction of rotation. This is one convention which is used for right hand system. The other way of visualizing is, if you look towards the origin from the positive direction of any axis, the direction of rotation will be counterclockwise for you. Okay? That means if you are looking towards me, let us say the origin is towards me, you are looking towards me from the positive z axis or positive x axis, whatever the case may be, and the direction of rotation will actually be counterclockwise for you. It will be counterclockwise for you. This also you can see from the figure that there are two ways of interpreting the positive direction of rotation. Either you grab the axis and then the fingers point to the direction of the positive part of the axis, the rest of the 4 fingers point to the direction of rotation, or you look down towards the origin. When you look down, you will see that it will actually be in a counterclockwise direction. You have to practice this yourself if you have not done so earlier in any course of 3-dimensional geometry or courses related to computer graphics. And come back to the screen, you will see this picture once again, the direction of the arrows. Now you see the circular arrows which are marking the direction of the rotation. And when you grab any axis x, y, z, the thumb pointing outwards, the rest of the fingers will point in the direction of the rotation, or you are looking towards the origin from the outside, you will see that the rotation actually is counterclockwise. Look into the z axis, look from the z axis positive towards the origin, you see counterclockwise. Look from x towards the origin, you see counterclockwise. Now, if you put that into perspective and come back to the figures at the bottom, so you are now looking from z towards the origin. On the left hand side figure, if you look at the rotation around the z axis, this is the counterclockwise rotation marked. Okay? So, you are basically rotating the object from x towards y. Okay? Remember that, and that is the convention of positive rotation based on which the signs, the polarity of the cosine and the sine alpha terms are basically used. Okay. Now, this is the rotation about the x axis. Rotation of the x axis will cause the counterclockwise rotation from y towards z. Okay. And also henceforth, rotation about y axis will cause rotation from z towards x. This is at par with the 3D system which you see on the top. I repeat again, rotation around z axis will cause rotation from x to y. Just remember these sentences and we will see why the sign comes out. Rotation about x axis will cause rotation from y to z, and rotation about y axis will cause rotation from z to x. Okay. So, if you follow and if you have understood the convention of rotation, the convention of positive rotation either by the thumb rule sort of a thing, or looking down towards the origin from the positive axis and then looking counterclockwise from positive rotation, then we will now look into the transformation matrix and see where the sign is kept to ensure that this consistency is kept in the 3 rotation matrices for rotation around z, around x and around y respectively. Here are the 3 rotation matrices once again. Okay. As you can see on the left hand side, I have put those 3 figures for you see the first column rotation around x axis y to z, rotation around z axis from x to y and rotation around y axis from z to x respectively. So, if you look at the first row, when you are rotating around the x axis, this is the corresponding transformation matrix. It will, the x coordinates is unchanged. So, that is why you have 1 0 0 on the first row, and you want the coordinates of y and z to change in such a manner that the rotation is taking place positively counterclockwise, or intuitively let us imagine from y to z, and henceforth these parameters cosine of alpha minus sin alpha cos alpha will cause rotation from y to z. Intuitively visualize yourself that this causes from y to z. If that is so, then rotation of around z axis from x to y, z axis from x to y will also cause this, where you have the 0 0 1 at the third row, where you do not want any change of the z coordinates of the object, you just want the x and y values to change. That means intuitively the rotation is taking place from x to y. From x to y, previously it was from y to z, now it is from x to y. Now, if you look at this around the y axis, the rotation which you want is actually z to x. If you want from z to x, not from x to z, to maintain the consistency of positive rotation. So, if you had put minus sign here, like as in the previous case, what would have happened is you would have forced a positive rotation to go from x to z. That would have violated the principle of right-handed coordinate system, the consistency of positive rotation or counterclockwise, whatever you have studied. If you had put the negative sign in the first row of the third matrix, that would have resulted in a rotation from x to z, but you want the rotation from z to x. If you want rotation from z to x, put the negative sign here. It is something like talking of actually a clockwise rotation, a negative rotation in some sense, to maintain the consistency. In the first case, I repeat, you want y to z, second case you want x to y, in third case you want z to x, not x to z. Since you want z to x, you have to put the sign here. First case, I repeat again, from y to z, so that is why y has the negative sign here, the second row. Second case around z axis, x to y. So, that is why the first row for the x axis has a negative sign. Here you want z to x, that is why the third row for z has a negative sign. I hope if you play this around yourself with the whole thing again, which we talked about in the last 10 minutes, starting from the right hand coordinate system, talking about gripping the axis, and talking about the thumb pointing upwards to the positive direction, the fingers pointing to the positive direction of the rotation, or looking down to the origin with counterclockwise convention of positive rotations. To maintain that consistency with respect to all the axes, you need to have one of the signs reversed for the rotation matrix. Any one sign reversal should have been okay. Here it is done for rotation about the y axis, which you want actually the rotation to happen from z to x instead of x to z. I repeat again, if you had put a negative sign here, like the previous two cases in the third matrix first row, if you have put a minus sign beta, you would have had a rotation from x to z, which you do not want. That will violate the consistency or right hand coordinate system when you want to rotate from y to z, then you want from z to x, and then x to y respectively. Now, that consistency is very, very important. So, that is the, so these are the three fundamental rotational matrices about x, y and z respectively. Now, if you remember in 2D transformations, we also talked about rotation about an arbitrary line, rotation and reflections about arbitrary lines and planes, and we first of all general, very special cases, and then we move to a general rotational matrix. So, in the next few minutes we will study about rotation about an arbitrary axis in space. Okay. So, what do we have here? Assume we want to perform a rotation by an amount theta about an axis in space, and now an arbitrary axis, because we have seen rotations about three specific coordinate axes x, y and z separately respectively. We have seen the forms. Now, we are talking about an arbitrary axis. Okay. You remember in 2D we talked about rotation about an arbitrary point in 2D. Here we have rotation about an arbitrary axis. Why an arbitrary axis? Yes, let us take the earth, it also rotates around the sun, it also rotates about its own axis, the moon also rotates about the earth. So, when you talk of rotation, you do not talk of rotation about only a point, as in the case you did in 2D. In 3D, you have an axis and you rotate about that axis. So, that axis was very specifically the orthogonal axis x, y and z respectively, the 3 corresponding axes in the right hand system. Now, if we have an arbitrary axis, the problem could demand to rotate about an arbitrary axis, and we need a mathematical formulation to rotate an arbitrary object or a point about an arbitrary axis in space. So, that is what we are studying now. So, again I repeat the problem as given in the slide. We want to perform a rotation by theta degrees about an axis in space, and that axis is defined by the following parameters. That axis passes through the point x naught, y naught and z naught, and it has its direction cosines of the axis. I will define what are the direction cosines. For the time being, assume they are something like cosine of a certain angle with respect to x, y and z respectively, and the direction cosines of that line are defined as cx, cy and cz respectively. So, there are 6 parameters which define a line uniquely. You need a point about which that line or axis through pass, and the direction cosines or orientation of that line. Once that line is uniquely defined, now we will try to rotate a point or an object about that particular axis. Okay. So, let us come back to the screen. These are the different steps which we have for rotation about an arbitrary axis in space. It is almost conceptually similar to what we did in 2D rotation about an arbitrary point. You remember what we did when we wanted to have a rotation about an arbitrary point? We translated the point to the origin, or origin was translated to the point, we did the rotation and then translated the point back. So, here you may have a few more steps, but actually if you see the steps 1, 3 and 5, translate, rotate and then undo the translation, actually it is the same as like in 2D. But since we have 3D here, there are 2 more steps, the second and the fourth steps, where we need to align the axis of rotation with respect to the coordinate axis, because in 2D we had the special form of rotation about the origin. So, that is why we brought the origin to the point. Here we have the form of the rotation matrix to rotate about an orthogonal axis, any axis x, y or z. So, now we need to first translate the line back to the origin or origin to the line, and then orient this axis such that it coincides with one of the axes. It could be x, y or z. Once we do that, we can apply our regular specialized rotation matrices and get the transformation done. So, let us read the lines, the steps of the algorithm. First of all, we need to translate by a certain amount, which is nothing but the x naught, y naught, z naught, the coordinates of the point about which the axis in space passes through. Next, we rotate the axis into one of the principal axis, and we will see why we pick up a rotation about the we actually do that by a rotation about x and y to coincide the axis with the z axis. And once the second step makes the arbitrary axis coincide with one of the principal axis, in this case it is z, we need to employ the rotation about by theta degrees about the z axis, and once that is done, we have to just undo the steps 2 and 1. In the opposite sense, you remember the matrix multiplication order is very important. So, the step number 4 says we undo the rotations to align the axis. That means whatever we did in 2, we just do the reverse operation, which can be done by inverse of the matrices, which we have already seen in 2D, and the last point of course undoes the operation done in step number 1 and or basically undoes the translation. So, these are the 5 steps, and typically I think we know step number 1, we know step number 3, that means we know the form of the matrices in these cases, and we know what it does, because it exactly does what we did for the case of 2D. We also know step number 5. Okay, because this is nothing but the inverse transpose or inverse translation of step number 1. Step number 2 is important, that is one which we have to solve, because if we solve step number 2, step number 4 is just an inverse operation of step number 2. So, once 2 is solved, we can get 4, 1, 3 and 5 steps are all known to us. So, we concentrate only on the operations to be done on step number 2, and then we can get all the matrices together and get the final form. Remember, so we go to the next slide where we concentrate on what to do for step number 2, which reads we rotate the axis onto one of the principal axis. In this case we pick up z, and that means we need to rotate by around x and y respectively. So, as I said before, that the tricky part of the algorithm is basically step number 2 as given before in the previous slide, and this is going to take us 2 rotations, one about the x axis. I will show you the figure why I say so, that you need to rotate the axis, arbitrary axis about the x axis to place it in the xz plane first, and then you rotate around the y axis to place the result considered in the z axis. Actually you can do the other way, nobody stops you from first rotating about the y axis to coincide it along say xz plane, and then you can do the reverse. Okay. So, let us look at the first step of rotation, which we said that you need to rotate around the x axis to put it back into the xz plane. If you remember that the previous example, I was saying that you need to rotate about the x axis to place the axis in the xz plane. Although it could be the other way around, where you can first rotate about y axis and then x, but we pick up x in this case. Okay. So, what does this mean? Let us look into this figure again. OP is the line. You can see in the 3D diagram, in the first in this course we have a 3D diagram. Although you are seeing it on a screen which is 2D, but you have to visualize this is a 3D diagram. You have to visualize x, z and y, the 3 perpendicular orthogonal coordinate system axis. You can start to imagine x is pointing towards you, y and z, and let us say the screen vertical and horizontal coordinate respectively, and OP is an arbitrary obliquely oriented axis about which we actually have to rotate. So, we have come to the stage where the origin is shifted to the some point on the OP axis, and now we have to do something such that this line or axis OP coincides with OZ. I repeat, we have to do 2 rotations to make OP coincide with OZ. Well, we can start thinking that it could be done by one rotation, but you have to do some mathematics which is equal to performing 2 rotations. Okay. So, OP has to be coincide with OZ, and that is done first by rotating around x axis, so that OP will first fall on the xz plane, and then you rotate around the y axis such that the projection of OP which has fallen onto the xz plane comes back to OZ. So, that is, so 2 steps of rotation of OP axis will bring that OP coincide with OZ. So, the first step is rotation of x by alpha. How do you determine that angle alpha? Now, you see I have projected the axis OP onto the zy plane, okay, onto the zy plane, and Cx, Cy, Cz are nothing but the direction cosine. So, assume that the OP is of unit vector in length, and the corresponding coordinate projections are Cx, Cy, Cz respectively, which are nothing but the direction cosines, and D is the diagonal or the length of the projection of OP on the zy plane. When you project OP on the zy plane, when you project it, remember, but what we are basically interested in, we are not going to actually project it is just a projection. That means, if I rotate OP by an amount alpha, let us say, which will bring OP onto the xz plane, it is equivalently you can visualize that this diagonal line which is marked as a distance d on the zy plane will coincide with the z axis. So, when you turn OP and coincide it with the zx plane, the line mark D will coincide itself with the OZ plane. That is what will happen. You are talking about positive rotation about the x axis, grip x axis, thumb pointing outwards or look towards the origin and visualize counterclockwise rotation. OP will now coincide with the xz axis, and D will actually fall on OZ, and that is what will happen, and that gives you the alpha. So, instead of measuring alpha directly from OP with respect to z axis, we can measure alpha from the diagonal line D with respect to z axis, and so we can see what is alpha. So, that was the step which you are talking about. Project the unit vector along OP onto the yz plane, and the yz components, as you seen in the previous figure, I hope you have drawn it on your notes already. We will also go back to that figure, it will come again, but the yz components of that projection after projecting onto the yz plane at Cy and Cz respectively, which are nothing but direction cosines of the unit vector along the arbitrary axis. We also talked about that, and it can be seen from the diagram that. I will give you the diagram and give you the equations. Once again, see the diagram here. Okay. So, we can see that D, Cz and the corresponding Cy. Okay. I can say Cz here, Cy and D, they form actually a right angle triangle. So, this helps to you to evaluate the value of D, okay, and that is given by the following expression. So, D is given by square root of or root over Cy square plus Cz square, or you can now actually evaluate alpha using Cz by D cosine inverse of sine inverse. Now, remember, we need both cosine and sine to evaluate alpha, not only its numerical value, but the sign. If you take only cosine or sine, due to the bipolar nature of the cosine and sine functions, either only cosine or sine will not give you the true value of the alpha, the sign of the alpha value, that means in which quadrant alpha is. You will have a problem. You basically need a combination of cosine and alpha. This is you can get from pure mathematics or trigonometric knowledge, that you need basically both cosine and sine alpha to actually get the sign and also the numerical value of alpha. Okay. So, we are looking at alpha, which can be obtained using sine inverse of this function. You can substitute D and you can get, that is the value of alpha which you get. So, now that means when you rotate the axis OP about the x axis by an amount alpha, the OP would be now lying on the x y. Okay. It will be lying along the x y plane. We will see that what it results in. This was the starting figure, if you remember. So, our I should correct myself that when you rotate OP around x axis in a counterclockwise fashion, it will fall on the xz plane, and we now know from the previous slide what is the value of alpha. And so, the stage after the first rotation will look like this. This is the new figure. After the OP has gone on to the new position, which is given by P Cx 0 D, that means the P has basically fallen on the xz plane. This will happen after the first rotation about the x axis. We now just need to rotate the OP axis about the y axis by an amount beta to coincide the OP axis with respect to the z axis. Remember, that was our target of step number 2. Step number 2 was to take the axis OP and coincide with the z axis. This was the first the second step of the general rotational matrix, and to do that, the first step of that second stage of the algorithm is to rotate about x, which will give us this particular scenario. So, alpha we know, now we need to just calculate beta. In fact, it is done almost in a similar manner. Since OP is a unit vector, you can imagine, and this length will still be the same, and since this is Cx, obviously this value has to be D. The D value which was here on the zx plane, this the projection of the OP on the zy plane is now nothing but the vertical coordinates of the or the z coordinates of OP after the projection, because root over c square plus d square should be equal to 1. Okay. So, what is the second stage of rotation? Rotate beta. Rotate about y axis by an amount beta. That is what, and how do we determine beta? The steps are similar to what we have done for alpha, and first is determine the angle beta to rotate the result about the z axis, and the x component is Cx and the z component is d, okay, and the cosine of beta is d divided by the length of the unit vector is equal to 1. Sin beta is this, and so beta can be evaluated using cosine beta and sin beta, and this gives us the Rx and Ry respectively for the second stage. The third stage is Rz, and the last stages are the corresponding inverse matrices. So, the final transformation of 3D rotation about an arbitrary axis is first translate along T, then 2 rotations about x and y given by the corresponding values of alpha and beta respectively, and once is Rx and Ry has been operated, what basically remains is rotation about the z axis by an amount theta, and this is step number 3, and then you have to undo what you have done earlier in terms of Ry and Rx. So, apply the inverse transformations and then apply the T. So, we are basically talking of post multiplication of the coordinates, and this will be the order. So, apply T first. If it is pre multiplication, the entire order will be changed. The leading matrix will be T and then Rx, Ry and so on. This is probably a case which I am talking about post multiplication of the point by the corresponding transformation. So, I write it again. You remember the steps: first translate, then corresponding 2 rotations, then the actual rotation of the theta, and then just keep undoing the 2 rotations about x, y and t respectively, okay, where the corresponding now I must give the form of those all these matrices here, T, Rx and Ry respectively. T is of course was given earlier to you, x naught, y naught, z naught, which was nothing but the point on the axis to where we had to shift the origin. Rx and Ry were obtained from the alpha and the beta, which we just talked about while trying to align OP axis, arbitrary axis OP with respect to z. So, you had Rx and Ry respectively, and these are the corresponding. Please write those equations and practice it yourself. Remember, Rx is a rotation about x, so the parameters occur in the second and third row and column. Rotation about y axis will keep the second element 1 and first row and third row and column elements as given by rotation about beta, and of course, the rotation about the z axis is the one where the actual rotation takes place about theta. So, once you get the first 3 or 4 rotations, you can know how to get Ry inverse, Rx inverse and T inverse is nothing but all these, this is the signs will change. The sign will change here in T, and in Rx and Ry, since they are orthogonal matrices of rotation as in the case of a 2D, you get the Rx inverse and Ry inverse to be the transpose. Will be the transpose of the corresponding matrices, and for the case of T, the sign will change. Okay. So, that is the general. I request you to come up with the general form of the matrix M by taking all these formulations of T, Rx, Ry into account, and it will give you a good practice of analytical algebra in terms of matrix multiplication and manipulation. Try to get the general form of the matrix M. I have purposefully not given it here. I leave it as an exercise for you for this particular chapter or lecture, that is, try to get the elements of M. You will have a 4 cross 4 16 elements of M, and try to get all the 16 elements of M from the by multiplying. You have about matrix multiplication, about 7 matrices to be multiplied, which are all given here. 3 of these, 4 of them are given here. The other 3 can be obtained by just the making the inverse of T, Rx and Ry respectively. So, that is how you get the generalized rotation about an arbitrary axis. I hope the concept is clear. You basically rotate, you translate the origin to that axis or take the axis back to the origin. Then what you do is basically give 2 rotations to align the axis with respect to the z axis. It could be x or y, but in this case I have taken z, rotate around z and just do the inverse of manipulations of the previous 2 stages to get back the final form. Okay. So, this is how it will look like. I am trying to make the matrix look slightly simpler. The generalized transformation matrix for rotation about an arbitrary axis, C and C inverse are nothing but T, Rx, Ry multiplication respectively. Special case of a 3D rotation, if you try to look at, we are looking at rotation about an axis parallel to a coordinate axis, say x axis. If you want to rotate, then you do not almost need anything. What you basically need to know is you need to translate the optical axis OP or the arbitrary axis OP to the origin, and the axis is automatically coincided with the x axis to apply the Rx rotation, rotate about y axis. A special case of 3D rotation, if you want to rotate about an axis parallel to say y axis, apply the same T, apply Ry and apply T. Rotate about an axis say parallel to z axis, well, T again RZT. So, these are the 3 special cases again of 3D rotations. If you want to rotate about an axis which are parallel to any one of the 3 coordinate axes, that is easy to visualize. On the top of the slide here, you can see you have the generalized expression given, and that has been the main part of the course today. I will stop with this lecture for the 1 hour, where we have started with 3-dimensional transformations. We looked at coordinate spaces first, we looked at specialized transformation matrices for translation, scaling, shear and then rotation, and the rest of the time we spent on trying to describe how to obtain a rotation about an arbitrary axis in space. So, please go through those transformations one again, draw those diagrams, write down all the equations of transformations, try to create. I left this an exercise to come out with the expression of the value of m for all the 16 elements, and that will give you a good grasp of the problem which we have discussed today. So, we will stop today and continue in the next lecture on the remaining set of transformations. Thank you very much.